So we have two methods in mind to find the optimum. So we would prefer the closed form, and the closed form doesn't require multiple iterations. Just said, let's take the derivative, ask at which point the derivative is 0, and voila, that's a great candidate to be the maximum, like the maximum likelihood. However, we sometimes cannot use this method, and that's why we need to use the iterative method that was depicted in this slide. And in this slide of going up the hills and being careful to not overshoot over the hills, probably making the steps smaller and smaller. And in this trouble, we also have to handle this multiple maxima, multiple minima part. But sometimes it's necessary. Like in this somehow toy example, here is f of x, it involves x times a of x, yada yada, and there is also x times minus 2 log x. What is the derivative of a product of two functions? It's the sum of the product of the first times the second plus the derivative of the second times the first. Derivative of log x is 1 over x. Do the calculation. F prime of x is ax minus log x. I want to make it equal to 0. It must happen to the derivative must be equal to 0 at the optimum, but unfortunately there is no closed formula to solve this equation. I can play with this numerically, but there is no closed formula. Same troubles that you face when you try to solve some of the polynomial in degree higher than 3. Even in 3 it's not convenient, and when it's higher than 3 then it's a whole nightmare. In many cases there is no such formula. Okay, so we understand the necessity to have both methods, and we would like therefore to find, once again, maximize the likelihood of the function. But finding the maximum sometimes, especially when I have it's very common when I write my maximum function that it consists of a product of two terms, like a product of one function x times one function of y. And I don't like this product of terms, definitely not when it's 2, and definitely not when it's many more than 2. So how can I resolve it? I just need two observations for it. I need to note that log, no matter which base it is, as long as it's larger than 10, log is a monotonically increasing function. If x1 is smaller than x2, then log of x1 is smaller than log of x2. So what's a big deal? It means that if I have some other function g of, say, y, and I'm looking for the point where g of y is a maximum, then log g of y is max if and only if log of g of y is max. The point that brings the maximum to the first also brings the maximum to the second. So log of x times y will just be replaced by log of x times log of y. Now it looks that log is more complicated. Log of x seems more complicated than just x, but in most cases we will see that we have some product of guys, especially when we'll go to Gaussians, and at this point we will use a function that if I take the log of an exponent of something, log of e to the power something, all I get is x in return, which will make it easier. At the moment, what am I trying to tell? That instead of maximizing the likelihood, let's maximize the log likelihood, and in many cases that would be simpler than just maximizing the likelihood itself. That is, we'll define a new function which is just a log, like log of the base e, of the old function. And once again, now we are trying to look for sigma hat, which is an argument. Argument, remember, is asking not what is the value of the maximum, but at which theta which value of theta, what a norm and standard deviation for which this form is a maximum. And if I have products of functions p1, p2, p3, then log of this product is nothing but the sum of the logs of each individual one. Now, so I want to find the derivative of the likelihood of n variables. It would be just compute the sum of the derivative of the log of individual derivatives. So far, I'm sure that I have not convinced you that I'm making anything simpler, but hopefully you will notice. So what's the flowchart so far? Decide on a model. Decide that you assume that all that the distribution underneath your experiment is, say, Bernoulli or Gaussian or uniform. Decide what the model, how the variables are depending on each other, or hopefully do not depend on each other, independent. And and in addition, check, decide about the model. Now you want to estimate the parameters, write out the log likelihood function, but is for every parameter how likely or unlikely it is, and state the optimal parameters are argmax of the log maximum likelihood, and calculate the derivative of the log likelihood function with respect to the parameters theta, each one of the individual parameters, and use some optimization algorithm to calculate this max. Okay, quick check. Moving along, let's take one individual example that is the Bernoulli variables. So I'm tossing a coin n times. The results are either 1 or 0, face or tail. The probability mass function, that is the probability that xi equal 1, is just p. Warning, p in the previous set of slides appeared as pi because we wanted to keep the letters distinguished. Now we'll just use p as a constant. It's not a function. So p of xi times 1 minus p to the power of 1 minus xi. What's the point? If xi is 1, then this probability is p. If xi is 0, then p to the 0 is 1, and 1 minus p to the power of 1 will be just 1 minus p. Likelihood here is, look at the list of result of your experiment, face, face, tail, face, 1, 1, 0, 1. Look at the likelihood, which is what? The product of the individual terms p of xi, what you get in this ith experiment, times 1 minus p to the power of 1 minus xi. Which is just this interesting expression that contains, collect all the xi's which are 1, so p to the power of all the xi's that are 1, and n minus all the xi's that are 1 leave us with 1 minus p to the power of all the tail, all the zeros that you get. Or other words, write s equal to the sum of xi, that ask how many faces did I get in the whole experiment, and it will be p to the number of faces they get times 1 minus p to the power of n minus number of faces, namely number of tails. Now pay attention, taking the log likelihood of this expression, log of this creature, using our experiment here, this formula that log of the product is just sum of the logs, is what it is. And another rule that tells us that log of a to the power of b equals b log a. We will also use this formula. So log of this expression will be the sum of the log of the first part plus n minus s, the sum of the logs of the log n plus a log of the second term, and now the s from here goes before the log, the b here moves to before the log, so it's s log p plus n minus s times log 1 minus p. So this is a log of the likelihood, and we want to find which value of p, that is what's the bias of the point, I should have said it a long time ago, what's the bias of the point, that will bring it to the maximum value, suggest the most likely experiment. So let's take the derivative of the derivative of this function. This function depends only on single parameter, p, of p, the bias of the coin, s log p. S is part of the data. I don't have control. I already got my sample point. That's why it's statistic and not probability. S log p plus n minus s log 1 minus p takes the derivative of this creature. If you're not familiar with this notation, that's d, still pronounced d, but it's special d that we are using only with respect to partial derivatives, or derivatives that are, in this case, just one parameter, but we'll use the same when there are more than single parameter. So derivative of the log likelihood d to dp, which is what? S times log p, the derivative of log of p, d to dp of log, is 1 over p. Just refresh your calculus memory. That's the stuff that you need to know for log of x. The derivative of it is 1 over x. And n minus s times log of 1 minus p. Here we are using the formula for a compound function, f of g of x. If we take the derivative, then what will be this function? Well, it's n minus s times the constants goes out, and it still becomes 1 over the internal function, so it's minus 1 over 1 minus p, and we want it to be 0. And solve it, we are getting that p at the maximum is nothing but what we all know ahead of time, but now we can prove it. What is the maximum p based on this formula? It's s, how many faces you got, divided by the number of n's, divided by n, the number of trials that you have. That's immediately from this formula, which is what we would all guess. If you had 73, if out of 100 trials you had 73 heads and 27 tails, then the probability of getting a head is 73 divided by 100. But that's finally a closed proof. Okay, moving ahead, let's talk about Gaussians. Now we're getting to the real world, because as we said, more things distributed as Gaussians. So x1 dot 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 xn each one is distributed as a Gaussian with the same, always the same average mu, same mean mu, and the same standard deviation sigma square, same variance. So what we want to find is, given all the data, tell me both what is mu and what is sigma square. What is our likelihood function? Again, we are assuming that these variables are IID, independent and identical distributions. So L of n is just, we need to remind ourselves what is a Gaussian, and what we need to remember from a Gaussian that it's more or less up to constant 1 over sigma times e to the minus x square over sigma square. The constants here are wrong, but beside it, it is fine, and that's actually the formula when the average is 0. If the average is not 0, then I just need to take all these functions and shift them, so make x believe that it is actually, when x equals 0, I want x to believe that it's actually at x equals 5. How? By subtracting 5 from all the xi's. So the mu just shifts all the graphs to the side. So I want to, my log likelihood is for each one of the variables. That's how I assume that it was distributed, and therefore the probability that I got these particular values, head, tails, or I sampled a set of people and measured their height, and that was the corresponding height, and I'll assume that height is distributed according to normals. What is the probability that that's the data that I have? It's just the product pi of the individual probabilities, which is what you see over here. And it, which I can write down as a which I can write down as, let's collect the 1 over sigma square. Maybe I want to double check it.